Welcome back to the Deep Dive. Our mission here is always the same. We take your complex source material, all the research, the books, the technical notes, and we turn them into accessible, unforgettable, and, well, actionable knowledge.
And today, the figure we're looking at is someone whose work is it's so fundamental.
It really is. I mean, if you're using any kind of digital device to listen to this right now, you are standing directly on the foundation he helped pour. We're talking about Brian Kernighan.
It's genuinely impossible to overstate his importance, and yet he's probably the least recognized giant of that early computing era, at least among the general public.
Right. When you list the foundational figures, you hear Ken Thompson, Ritchie, the big industry titans later on.
But Kernighan is the quiet architect. He's the essential guide. He didn't invent the C language, for instance, but his initial, the K, is synonymous with its defining book, K&RC.
And he didn't invent the operating system itself, but he coined the term Unix.
That's it. That's the perfect distinction.
So that's our goal for this deep dive. We're going to unpack the legacy of this man, focusing on the tools he built at Bell Labs and the programming philosophy he codified and really taught to the world, a philosophy that fundamentally changed how programmers think.
Exactly. I mean, the source material shows this incredible career. He's 83 now, born in 1942, and he's still an active professor at Princeton.
Since 2000. That's incredible.
He's a living bridge. He connects the very birth of modern computing in the 60s with the wild digital ecosystem we're all swimming in today.
That bridge analogy is perfect because his work spans both the tech innovation side and the teaching side, the pedagogy. It's not just academic history. It's the operational DNA of massive, massive systems.
Absolutely. Just think about Unix, a system he helped name and popularize. It powers everything from your phone to massive servers to scientific computing clusters.
Everything.
But beyond the systems themselves, Kernighan provided the methodology, the clear, practical approach to writing good code, which he championed in his software tools series. He is, above all, a synthesizer, a communicator. He takes these pioneering, complex tools and makes them usable for millions of people.
Okay, so let's unpack this incredible journey. Let's start right at the beginning. At the genesis of his career. We'll look at his academic roots and that pivotal environment at Bell Labs because we need to find out where the K factor in modern computing really began. So Kernighan is Canadian, and he starts his academic path at the University of Toronto, getting a degree in engineering physics from 1960 to 64.
And then he moves south to Princeton for his PhD in electrical engineering, which he finishes in 1969.
And I pulled the title of that dissertation. It is a bit of a mouthful, but it's so important. Some graph partitioning problems related to program segmentation.
That title might sound completely esoteric, but honestly, it's the Rosetta Stone for his entire career, graph partitioning. It's all about efficiency and structure.
Okay, can you ground that for us a bit?
Mm-hmm.
Why is breaking up a graph relevant to writing a computer program?
So think of a graph as a network, right? A set of nodes and connections. A huge computer program can be modeled as a graph where you have functions and data flows all connected.
Okay.
Partitioning is the art of breaking that massive, messy structure into smaller, more manageable pieces. And the key is you want to do it while minimizing the number of connections, the cuts between those pieces.
So you're making it modular.
Exactly. And in practical terms, this translates directly to efficiency in, say, laying out a microchip or organizing software, like segmenting memory or breaking a big program into modules that can run more or less on their own.
So even before he was writing the books that taught the world how to program, his mind was already focused on optimization and structure, on how to take a complex problem and break it down into the most efficient parts possible.
Precisely. His mind was just built for systems analysis, and that focus is the perfect setup for his next move, to Bell Labs, which in the late 60s and early 70s was arguably the most important place on the planet for shaping the future of IT.
And he's working there right alongside the titans, Ken Thompson and Ritchie.
Can you imagine? The environment must have been absolutely electric. Thompson and Ritchie are building what will become the world's most influential operating system.
But our sources point to a huge, and like you said, often overlooked contribution Kernighan made right at the very beginning of that project.
Yes. While they were building the technical backbone, Kernighan was doing the essential work of definition and promotion. And this is the key fact. Kernighan coined the term Unix.
So what was it called before?
The system started as Unisys, which stood for Uniplexed Information and Computing Service. It was sort of a satirical jab at the huge, unwieldy multi-TCS project they'd worked on before.
So Unisys was clunky, Maybe a bit of an inside joke.
It was. Kernighan saw an opportunity for clarity, for branding even. He shortened it, refined it to Unix. It gave the system this memorable, strong identity that set it apart.
But it was more than just a name change, wasn't it?
Oh, much more. He was also instrumental in helping Thompson and Ritchie articulate and popularize the Unix philosophy.
The idea that programs should do one thing, do it well, and work together.
Exactly. Using common interfaces like pipes. That whole philosophy became the operational ethos for an entire generation of computing. He didn't just write code. He effectively branded the entire concept of structured, modular, small tool computing.
That role of popularizer, of communicator,
Yeah.
it seems to be his specialty.
It absolutely is. He saw the revolutionary ideas underneath and helped articulate them both in memos and, crucially, to the wider world. He was the perfect guide to introduce these new ideas to an audience that had grown up on, giant mainframe computers.
And that guiding role leads us directly to the book that defined a generation of programming, the C programming language, which he co-authored with Dennis Ritchie, the book that gave us the term K&RC.
That book wasn't just a book on C. For over a decade, it was the definitive specification for the language. This was before any formal standardization.
So if your compiler could build code, according to the K&R book, it was considered a legitimate C compiler.
That was the standard. It was, in essence, the C language Bible. And it was responsible for C's explosive adoption in universities and industry.
But here's a crucial nuance that just speaks volumes about Kernighan's humility. Despite his initial being right there on the cover, he explicitly said, and I'm quoting, that he had no part in the design of the C language. He was crystal clear. It's entirely Dennis Ritchie's work.
And that's vital context. It really highlights the nature of their collaboration. Ritchie was the linguistic architect. He created this low-level, powerful, but remarkably simple language.
So what was Kernighan's genius then?
It was in the pedagogy, the articulation of how to use C effectively. He provided the clear examples, the structure, the style guides, all the things needed to take C from a Bell Labs project and turn it into the global standard for systems programming.
So the K in K&RC and later in AWK, it stands for Kernighan, the great communicator, not Kernighan, the language designer.
Perfectly put.
Yeah.
And in that role as communicator, he gives us maybe the most ubiquitous piece of code in history. Hello, world!
We all just take it for granted now. It's the first thing you type.
Ugh.
But that specific ritual comes directly from his work.
It's a foundational cultural artifact of computing. And the origin goes back to 1972, even before C really took off. He wrote a document called A Tutorial Introduction to the Language B.
B being the immediate predecessor to C.
Right. And he wasn't trying to create some grand ritual. He was just trying to provide a clear, minimal example.
Of what? What was he demonstrating?
Memory management and strings. He just needed a simple, unambiguous way to show how to declare a string, store it, and print it out. So he used the phrases hello and world as simple variables to illustrate it.
And that just stuck.
It stuck. It became the iconic starting point, the minimal proof that your entire development environment, your compiler, your OS, was all set up correctly and ready to go. It became the universal rite of passage for every new programmer.
It's the simplicity that made it so enduring. Every programmer knows that little feeling of triumph when they see those two words print out.
Absolutely. And here's a fascinating little anecdote from the source material that shows how much status that simple phrase has. Kernighan's original 1978 implementation of the program, the actual code, was deemed so significant that it was sold at the algorithm auction.
Wow, they sold the code for Hello World.
Think about that. That's recognizing a piece of code as a true historical artifact, like a famous painting or a manuscript. It just underscores that these aren't just dry technical concepts, they are the bedrock of our digital civilization. And it all came from Kernighan trying to clearly explain string handling.
The man gave us the name for the operating system, defined its programming language, and gave us the introductory phrase for every developer. Okay, so now let's move from those iconic roles to the specific tools he engineered that made the Unix ecosystem so productive. We're transitioning now from the big picture systems to the specific languages Kernighan co-authored. And let's start with AWK.
Right, AWK. The name is an acronym for the three authors, Alfred Aho, Peter J. Weinberger, and of course, Brian Kernighan. It was developed in 1977.
And it is the quintessential Unix utility.
It's a fantastic example of that Unix philosophy in practice. It's a specialized language, a domain-specific language, optimized for one thing, text processing, data extraction reporting. It's a little powerhouse.
So if you have a massive log file or a huge CSV and you need to pull out specific columns and summarize the data,
AWK is your best friend. A lot of people today might default to, I don't know, Python, or maybe even try to load it into a spreadsheet.
which will probably crash. So why does AWK, a language from 1977, still matter so much? What makes it unique?
Its power is in its simplicity and its implicit structure. AWK automatically reads your input line by line. For every single line, it automatically breaks the data into fields based on a delimiter, like a space or a comma.
So you don't have to write all that boilerplate code for looping and splitting?
None of it. You just define patterns and actions. You can just say, for every line where the first column says error, print the third and fifth columns. That's it. It's incredibly fast and efficient for slicing and dicing structured text, often much faster than firing up a more general-purpose language.
It perfectly embodies that idea of a small tool doing one thing incredibly well.
Absolutely. The book, The AWK Programming Language, came out in '88, and it's so relevant that it was reissued in 2023. But here's the fact that just defines Kernighan's commitment.
I think I know what you're going to say.
Our source material notes that as recently as 2022, he stated he was actively working on improvements to AWK.
The man is in his 80s, and he's still maintaining and curating a 45-year-old programming language. That is just astonishing dedication.
It's stunning. Most software from that era is completely obsolete. The fact that he is still actively improving AWK shows you how durable and elegant, robust tool design can be. It proves that simplicity and focus in software can endure far longer than, these massive, complex frameworks built on whatever the trend of the day is.
That structural thinking, that focus on optimization, it didn't stop at text processing. In the mid-'80s, he co-authored AMPL, a mathematical programming language.
And this takes us right back to his PhD dissertation, doesn't it?
It really does. Back to graph partitioning.
AMPL, from 1985, is designed for describing and solving large-scale mathematical problems, optimization problems, linear programming, nonlinear integer programming, all that heavy-duty stuff.
So what's the real difference between a traditional language like C and a mathematical language like AMPL?
A traditional language tells the computer how to get a result, step by step. AMPL is a modeling language. You describe the problem. You describe the constraints, the objective, what you want to maximize or minimize, and the language then interfaces with specialized solvers to find the optimal solution for you.
So instead of writing the optimization algorithm yourself, you're just modeling the problem and letting the system figure out the best path.
Precisely. It lets the experts, the mathematicians, the engineers focus on the structure of their problem, not the boilerplate code needed to manage memory or loop through data. It just shows his incredible range. He's equally comfortable writing elegant prose to teach C and designing these precise formal languages for high-level optimization.
Speaking of optimization, let's pivot to his foundational work in algorithms, especially his collaboration with Shen Lin on these really hard NP-complete problems.
Right. And their algorithms bear their names, but with this fascinating example of professional equity in how they're named.
Let's get into that. But first, can you give us a quick refresher on NP-complete problems?
Sure. They're famous in computer science because they are computationally hard. Things like the traveling salesman problem or graph partitioning. For any really big version of these problems, finding the absolute, provably perfect solution is often impossible in a reasonable amount of time, even for a supercomputer.
Can you give us a quick, tangible example of the traveling salesman problem?
Absolutely. Imagine a delivery driver. They have to visit, say, 50 cities. Start at the hub, visit every city exactly once, and return to the hub. The goal is simple. Find the shortest possible route.
Sounds simple enough.
But the number of possible routes grows factorially. For 50 cities, the number of routes is astronomical. You could never check them all. This is where heuristics come in. You need a clever way to find a really good answer, even if it's not provably the single best one.
And that's where Kernighan and Lin stepped in, with practical, efficient solutions.
Yes, two major contributions here. First, we have the Kernighan-Lin algorithm from 1970. This goes back to his PhD. It addresses graph partitioning, dividing a graph into two pieces of roughly equal size while minimizing the connections between them.
Which is vital for things like designing a circuit board,
Right.
minimizing wire length.
Exactly. Then, a few years later in 1973, they gave us the Kernighan heuristic. This is a powerful method for tackling the traveling salesman problem itself.
Okay, so why the different name order? Kernighan-Lin versus Lin-Kernighan.
It's subtle, but it's a powerful display of, authorial equity, professional courtesy. The Kernighan-Lin paper came first and addressed the problem directly related to Kernighan's own PhD focus. That's likely why his name is first.
And then for the second paper.
For the second, equally famous paper on the traveling salesman heuristic, they reversed the order. They put Lin's name first.
So even though they were working on similar problems, they made sure to balance the credit instead of, say, always listing the better-known name first.
Precisely. It's a wonderful reflection of the intellectual generosity in their collaboration, and both algorithms are foundational. The Lin-Kernighan heuristic, in particular, is still one of the most effective methods for quickly finding near-optimal solutions to the TSP. It's essential for logistics and routing today.
Okay, moving beyond the core languages and algorithms, Kernighan was also instrumental in building the tools for documentation and publishing within Unix, the stuff we barely think about now.
These tools were absolutely essential. Remember, Unix was built by scientists and engineers. They needed to write papers, manuals, technical reports.
And they needed to include math, diagrams, precise formatting.
And they needed to do it all without leaving the command line.
Let's break down the three main tools he co-created. First up is ditroff.
Right. Ditroff, from around 1973, stands for Device-Independent Troff. Troff was the original text formatting program, but it was hard-coded for specific output devices.
So a specific printer or typesetter.
Exactly. By making it device-independent, Kernighan made it so the same source file could produce identical presentation-quality output on virtually any device. It was a revolutionary concept for portability at a time when hardware compatibility was just a nightmare.
And then there's Equin, which he created with Lorinda Cherry in 1974.
Equin was the typesetting language for mathematics inside of Troff. Before this, getting a complex equation into a document was just a manual, tedious, messy process.
Right.
Equin let scientists write expressions in a simple, almost plain text way, like a over b plus c sub 2, and the system would handle the precise layout of the fractions, the superscripts, everything. It completely streamlined scientific publishing at Bell Labs.
And finally, a tool for visuals, PIC, in 1988.
PIC was for diagrams. If you needed a flowchart, a system schematic, any simple diagram for your manual, you used PIC. You described it with text, and it drew it.
So if you put them all together, ditroff for formatting, Equin for math, PIC for diagrams, Kernighan helped create a self-contained command-line desktop publishing system decades before most people had a desktop computer.
Precisely. It shows a holistic approach. A perfect system needs good code, but it also needs good documentation. And the tools he built ensured that the documentation was as rigorous and professional as the software itself.
And that brings us from the tools themselves to the philosophy behind them. Because Kernighan wasn't just building things, he was teaching people how to think about programming, no matter what language they were using. The core ethos of that Unix world was really spread globally through Kernighan's teaching, especially his software tools series, which he co-authored with PJ Plogger. What was the central mission of that series?
The mission was all about portability and methodology. In the 70s, a lot of places, universities, corporations, they were heavily invested in older languages like Fortran. And Fortran lacked a lot of the structured programming features we just take for granted today. Kernighan and Plogger realized that the power of Unix, the modularity, the structured control flow, the reusability, that power wasn't tied to the C language. It was a way of thinking.
So the books didn't just teach C, they taught the style of C thinking, even if you were stuck writing in something older and less flexible.
Exactly. The software tools books were like blueprints. They provided adaptations so that programmers using these older languages could adopt that structured modular approach that was pioneered in Unix. They made versions for BASIC, Fortran, Pascal.
And the most famous example of this was RAT4, right?
Oh, RAT4 was a revelation. It stands for Rational Fortran. Standard Fortran at the time was notorious for spaghetti code because it relied so heavily on JOTO statement.
Jumps all over the place.
A total mess. RAT4 was a preprocessor. It let programmers use clear, modern, structured concepts. Things like if and else, while loops, break statements, things that were natural in C but really clumsy or impossible in standard Fortran.
And then what happened?
The RAT4 program would then compile those structured statements down into legitimate, portable Fortran code that any standard compiler could understand.
So it was a way to introduce good software engineering principles without telling a huge company they had to throw out millions of lines of Fortran code.
It was a brilliant Trojan horse for structured programming, and they put it in the public domain. They made it freely available, so they spread these disciplined coding practices all over the world, promoting portable, readable code. It just shows his priority was always the methodology, not language tribalism.
But despite that, he clearly had a favorite. Which brings us to a great anecdote, the Sea Island test.
Yes, he famously asked the question, if you were stranded on a remote island and could only bring one programming language with you, which one would it be?
Kernighan's answer was C.
It was C.
So why C? Why not something newer, safer, or even a high-level tool like his own AWK?
The choice goes right back to C's foundational role. Its combination of simplicity and raw power. C is what we call close to the metal. It gives the programmer explicit, direct control over memory, over system resources, over hardware.
It's the language you'd use to build a system from absolute scratch.
Precisely. If you're bootstrapping a new digital world on this metaphorical island, you need a language that can write the operating system kernel, the compiler, the fundamental tools themselves. C provides that minimal, powerful tool set to do exactly that. It's the language of creation. His choice just reflects this deep, engineering-driven understanding of what makes a system work from the ground up.
Okay, so moving from the practical to the more philosophical, we get to a term Kernighan coined that is just a brilliant, biting critique of modern interface design. WYSIAYG.
What you see is all you get. This is a phenomenal piece of critical design philosophy, and it's maybe more relevant today than it was when he coined it.
We're all familiar with WYSIAYG. What you see is what you get. That describes things like a traditional word processor, where the screen is supposed to look exactly like the printed page.
Right. But WYSIAYG, his sarcastic version, is the critical contrast. He's making a point about what's missing, what's being stripped away.
So what's he getting at? What's been thrown away?
He's criticizing the tendency of purely visual interfaces to hide, or worse, completely discard the underlying structural or semantic information that gives a document its utility in other contexts.
Can we illustrate that with a modern example?
Sure. Think about writing a document. If you write it in a structured format like Markdown or LaTeX, you explicitly define your sections, your lists, your headings using clear source code. That's pure structure. You can easily export it, index it, transform it into a dozen different formats.
And the WYSIAYG alternative.
If you write the same thing in a purely visual editor, say Google Docs, you might just highlight some text and click the bold button. You see the result, bold text, but the system underneath might just be storing this text is visually emphasized.
It doesn't know it's a heading.
Exactly. It might have thrown away the semantic distinction between a section heading and just some large, bold text you used for emphasis. You only get the visual appearance, you lose the structural definition.
What you see is all you get. And what you get isn't enough for any kind of automated processing.
That's it. Kernighan's critique forces us to ask, are we prioritizing visual ease right now at the expense of structural utility and flexibility down the road? And that insight is crucial for everything from document management to modern web development.
On the topic of critique, we have to mention his famous takedown of another major language at the time, Pascal. It was in a 1981 technical report called Why Pascal is Not My Favorite Programming Language.
This was a very popular and definitely a provocative piece of writing. It really stirred things up in the academic world because Pascal, designed by Nick Lusworth, was praised academically for its rigor and for promoting structured programming.
The very thing Kernighan was advocating for. So if it championed structure, why was he so critical?
His critique was all about its limitations in the real world, in the large-scale systems environment of Bell Labs. He pointed to rigidity in how it handled strings, a clumsy approach to input and output, and its limits on building large portable systems that had to interact cleanly with the OS.
All the things that C was really good at.
Precisely. He basically argued that while Pascal was a great language for teaching computer science concepts, it was often inadequate for production engineering, for building real things that had to work in the wild.
Was the criticism just an intellectual jab, or did it have an effect?
It was constructive critique rooted in engineering reality. And it did have an effect. The sources note that some parts of his criticism actually became obsolete because the ISO standard for Pascal was created after his report came out, and it addressed some of the flaws he'd highlighted.
So his expert critique helped spur the evolution of the language.
It's a great example of how strong, informed opposition can actually lead to progress in a technical field. It's clear that whether he was building a tool, writing a book, or issuing a critique, his central goal was always the same: improve the efficiency, the clarity, and the structural soundness of programming.
He is the ultimate engineer communicator.
That's the perfect summary.
Let's move now to the latter half of his career, when he moves from the industrial research powerhouse of Bell Labs to the world of academia. He's been a professor of computer science at Princeton since 2000, and he's the director of undergraduate studies.
And Princeton gained an immense resource. His role as an educator is maybe the most enduring part of his later legacy, especially his commitment to outreach beyond computer science majors. Every fall, he teaches this highly influential course called Computers in Our World, COS 109.
Teaching the fundamentals of computing to non-majors feels more important now than ever before.
Oh, it's absolutely crucial for digital literacy. The course focuses on the core concepts. How does the internet actually work? What does privacy really mean? The mechanics of cryptography, security risks.
All the stuff we interact with daily but don't really understand.
Right. And to have a course like that taught by a foundational figure, someone who can give an authoritative, non-technical explanation, it's just invaluable.
And the course material isn't static either. It's not like he's been giving the same lectures since 2000.
Far from it. The sources note that while the core structure, the fundamental principles of computing stays the same, the lectures and the examples are updated every single year according to what's happening.
So if there's a major data breach or a new development in AI,
he's weaving it in. He's constantly relating these decades-old fundamentals back to the immediate contemporary world. It keeps the material grounded and relevant.
and his influence as an educator extends far beyond Princeton, reaching millions through a connection to probably the most famous introductory course in the world, Harvard's CS50.
This connection is really fascinating. It links Kernighan's teaching style directly to the modern era of massive online learning. So back in 1996, Kernighan actually taught CS50 at Harvard.
And why is that specific year so critical?
Because one of the people who was deeply familiar with his teaching approach then was David J. Millen. Millen later took over teaching CS50 and built it into the global phenomenon it is today.
The one that's offered online for free to millions.
The very same. It runs at multiple universities. It's become the de facto standard for introducing people to computational thought, and Kernighan helped define the pedagogical DNA of that course.
So it's a direct continuation of that synthesizer and popularizer role we saw at Bell Labs, just applied now to mass education.
Exactly. He defined the model for how to teach the fundamentals in an effective, engaging way. And of course, his contributions have been formally recognized. He was elected to the National Academy of Engineering in 2002 and the American Academy of Arts and Sciences in 2019.
These honors really underscore that his work transcends any one technology. It's about engineering methodology, about establishing foundational principles.
And we have to talk about his later books. His bibliography is practically a history of computing in itself.
Right. After the early foundational books, he had this very fruitful collaboration with Rob Pike, another Unix giant. They wrote the Unix Program and Environment in '84, and then The Practice of Programming in 1999.
And he remained so current. I mean, think about this. In 2015, he co-authored the Go programming language.
Go, the modern systems language developed at Google.
Developed by Rob Pike and others, yes. The fact that Kernighan was involved in writing the standard text for a brand new modern systems language just shows his enduring relevance.
But his focus also shifted dramatically toward explaining technology to non-specialists, reflecting that teaching role at Princeton.
His later books are all about digital literacy. D is for Digital in 2011, Understanding the Digital World in 2017, and one of my favorites, Millions, Billions, Zillions, Defending Yourself in a World of Too Many Numbers.
These books really cement his role as a public intellectual. He's trying to demystify data and technology for everyone.
He's using his authority not just to teach programmers how to code, but to teach everyone else how to critically understand the world that code created.
And then, in a fitting culmination, he brought the story full circle. In 2019, he published UNAX, a history and a memoir.
His own personal account from the epicenter. It's the final piece of the puzzle. The quiet architect reflecting on the massive structure he helped name, define, and popularize. It's a body of work that spans 5 decades and covers every single facet of computational practice.
So if we synthesize this deep dive for you, the listener, We started with the birth of Unix and C. We moved through foundational algorithms like Kernighan and Lin, explored that critical programming philosophy from the Software Tools series, and then we examined his incredible influence on education. He defined the tools, the standards, and really the style of thinking that enabled the internet age.
Kernighan's legacy really exemplifies a crucial truth in technology: true foundational contributions. They're often not in the biggest, flashiest breakthroughs. They're found in the clarity of communication, the strength of methodology, and the elegance of small, reusable tools. He is the ultimate expert guide for the field.
And the thing that stands out most to me is the commitment, that constant curation and maintenance.
It's the single most enduring statement about the value of simplicity and structure. I mean, just look at the key facts again. The person who helped invent the concept of the Unix operating system and wrote the definitive book on C is, right now, in his early 80s, still actively fixing and improving a 45-year-old programming language, AWK.
So what does that tell us about the current state of software?
Well, it raises a really important question for modern developers and users. What does it mean when these fundamental systems that started it all, like AWK, still possess an elegance and reliability that our modern, often bloated, incredibly complex frameworks struggle to match?
It suggests the guiding principle, small tools doing one thing well, has a longevity that just outstrips rapid iteration and massive scale.
It really does.
And finally, building on his brilliant WYSIAYG critique, what you see as all you get here is something for you to mull on this week. Consider the tools you use every day: your document editor, your web framework, your CRM system.
What vital piece of structural information or semantic definition or just underlying clarity might you be missing in your daily work? What might have been thrown away by that modern, glossy WYSIAYG system just to prioritize immediate visual appearance over long-term utility and flexibility?
Are you sacrificing future portability for immediate ease of use? That's a powerful thought.
Think about that trade-off, that fundamental choice between structure and veneer. That is the essence of Brian Kernighan's philosophy.
That's it for this deep dive. We'll see you next time.